In this illustration, we'll study how to calculate the force between skew lines which are charged. The problem given in this illustration is two mutually perpendicular long straight conductors carrying uniformly distributed charges of linear charge densities lambda1 and lambda2 are positioned at a distance a from each other, and we are required to find the interaction force between the rods. Let's solve this illustration. In this situation, there is one rod which is uniformly charged with a charge lambda2 coulomb per meter, and as the two rods are mutually perpendicular and separated by a separation a, so this is the another wire which we can consider. Here I am taking this wire to be plane perpendicular to the plane of this paper. Here this is the one which is uniformly charged with the charge density lambda1, and this is the rod which is placed in the plane perpendicular to the first one at separation a. And here we are required to find the interaction force between these two rods, and we can treat these conductors to be long because it is given in the problem. Here, to calculate the force on the second conductor due to the first conductor, we consider an element at a distance x, which is of width dx, from this point O. I am taking this point O as the center of the second conductor. Now, due to the first conductor at this point, there will be an electric field in radially outward direction, and due to that electric field only, this element will experience a force. So, if I calculate the force on element on conductor 2, this is conductor 1 and this is 2, force on element on conductor 2 due to conductor 1 is, here this force dF we can write as dq multiplied by E1, where dq is the charge on this element and E1 is the electric field due to this conductor at this point. So if this distance is r, then here electric field at this point E1 we can write as 2k lambda 1 by r, where k is 1 by 4 pi epsilon naught. So in this situation, if I substitute the values dq, we can simply write as lambda 2 dx, and E1 we can write here as lambda 1 by 2 pi epsilon naught. This distance r we can give as root of a square plus x square. And in this situation, if this is the force experienced on this element, if this angle is theta, this will also be theta. So this force will be having two components. One is the upward component, that is df sine theta. Another is the component in horizontal direction, which is df cos theta. So in this situation, you can see if we consider a corresponding element on the other side, df sine theta gets cancelled out and df cos theta will be added up. So here we can write total force on conductor 2 is, here this total force can be given as integration of df cos theta. So if we substitute the values, here the value of df will be lambda 1 lambda 2 dx by 2 pi epsilon naught root of a square plus x square, and in this triangle we can substitute the value of cos theta as a by root of a square plus x square, and as the conductor is long, we'll integrate it within limits from minus infinity to plus infinity. Here constants we can take out of the sign of integration, which are lambda 1 lambda 2 a by 2 pi epsilon naught. This is integration of dx by a square plus x square from minus infinity to plus infinity. And here there is a standard integration which we can write as lambda 1 lambda 2 a by 2 pi epsilon naught. Integration of 1 by a square plus x square can be written as 1 by a tan inverse of x by a, and we substitute limits from minus infinity to plus infinity. And on substituting limits, you can see here we are getting lambda 1 lambda 2 a by 2 pi epsilon naught. Here we can cancel this a also, as these two a gets cancelled out, and tan inverse infinity is pi by 2, tan inverse minus infinity is also minus pi by 2. So this will become pi by 2 plus pi by 2. And this pi also gets cancelled out with this pi. So final result we are getting is lambda 1 lambda 2 by 2 epsilon naught. This is the result we are finally getting, and that will be the answer to this problem.